Good morning everyone, welcome back to our channel Study with Adu. So today, before watching the video itself, like the video, comment your opinions, doubts, suggestions, etc, and for sure I'll be replying to it. And subscribe to my channel, like the video once again, and enable the bell button for all the videos. So now we are doing we did the organic chemistry series and we are doing the physical chemistry series. In between, now we are having some we are starting with one more series, that is the inorganic chemistry series. So inorganic chemistry full revision series. Okay, so first there are how many chapters? There are many chapters in inorganic chemistry. That is periodic table, that periodic classification, then chemical bonding, P block, D block, D and F block, and coordination compounds and coordination chemistry. These are the important chapters. The thing is that only 5 chapters are there. In that periodic table we'll be not revising, because if you revise D and F block and P block itself, periodic table will be for sure set for you. So no need to revise that. But we will be only revising these 4 chapters, and we'll be starting with D and F block, then coordination, then we'll be going to chemical bonding, and at last P block. Okay, so first we'll be starting with D and F block elements. D and F block elements. Only the important concepts will be telling. We have to fastly end the chapter, so D and F block elements, the important concepts will be discussed. D and F block elements. First of all, they are telling what are transition elements and what are in transition what are inner transition element. First of all, what is transition metal? Elements with the incomplete d subshell in their ground state or in any of their common oxidation state. So example is like, look, when you consider Cu, copper, the electronic configuration of copper is 1 2 3 4 5. That is scuti-V-crimin and fico-nicusin. You know that a pairing will happen. So this is the electronic configuration of copper. Look here in its ground state it is fully filled, but in Cu2 plus state we have incomplete subshell. Therefore Cu is a transition element, because in its oxidation state incomplete d subshell, because in one of its oxidation state its d subshell is what? Its d subshell is incomplete. Perfect. Yes. But I have to ask you, zinc, the electronic configuration of zinc is this fees concession for needing discussing 1 2 3 4 5. This is the electronic configuration of zinc, and the common oxidation state of zinc is Zn2+. That is, from S we'll take 2 electrons. Here also the S subshell is incomplete, but D subshell is completely filled. So therefore zinc and its group, that is zinc, mercury and all, that is which all elements, once again let me check. Therefore the elements zinc, cadmium and mercury are not transition elements. They are not called transition elements, but they are just D block elements. They are not transition metals. Okay, they are not transition metals because they don't have incomplete D subshell in any of their states. Okay, so this is the first thing we should regard. Okay. now we are going to learn about inner transition elements, that is what? Yes, inner transition elements are F block elements or lanthanoids and actinoids. Okay, perfect. So these are the two types. Now we are coming into specially we are going to coming into the D block elements. Okay, first of all, position in periodic table. Look, this is your periodic table. Hydrogen is placed here. Somewhat like this our periodic table look, and we have the F block here. Okay, and the D block is placed here. This is called the D block, and F block is placed below. You take an arrow like this and place it, that is like this arrow. This is F block. This is which block? This is S block. This is a common idea I am giving it. This much is which one? D block. Okay, yes. So D block is present here, F block here. Okay, so D block position I told you. Now we have electronic configuration. You should learn the electronic configuration of the first period, that is period of scandium configuration. Everything should be by heart. Electronic configuration of scandium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. These 10 elements electronic configuration should be by heart. Okay, so let us write the electronic configuration. Scandium, atomic number 21, electronic configuration is 4s2 3d1. Now scandium, titanium 22, 4s2 3d2. Yes, titanium. Vanadium, it is 23, 4s2 3d3. Chromium, it is 24, 4s2 3d4. No, it is 4s1 3d5. Why it is arranged like that? Because for getting half filled configuration in D and S, both are having half filled, more stable. Now what? Manganese 25, that is 4s2 3d5. Now manganese iron 26, that is 4s2 3d6. Now iron. Cobalt 27, that is 4s2 3d7. Nickel 28, 4s2 3d8. Nickel over. Now cobalt, nickel, copper, it is 29, it will be 4s1 3d10. Last but not the least, zinc. It is not a transition element, but it's a D block element. So 4s2 3d10. This is the first transition series. Okay, yes. Learn about this. Learn on this. Okay, perfect. Now in the second transition series, this series also we will just go through. Okay, first we have yttrium, that is 39. Yttrium 39. Yttrium 39, electronic configuration 4s2 3d1. Then zirconium 40, it has 4s2, one second, not 4s, sorry, 5s2 3d 4d1. This is 5s2 4d2. Yttrium, zirconium, nibedium, Nb. It's nibedium itself, right? One second. You know, really, this is very confusing. Nb, okay. Nibedium, I remember it as nibedium. Look, the name of the compounds are really confusing to me. It will become 5s1 4d4. This is different. We prefer it to be 5s2 4d3, but it is 5s1 4d4. Now next one is molybdenum 42, 5s1 4d5. Next one is the odd element. Next one is an odd element, that is technetium. We prefer it to be 5s2 4d5, right? But it is 5s1 4d6. It skips its stability, a half-filled d orbital, and goes to d6. And this element has another specialty. Technetium is the first man-made element. Okay, now we have next one, rudium, that is 44, 5s1 4d7. Then rhodium, that is 45, that is 5s1 4d8. Next one is what? Palladium. Palladium is another odd one, 46. It has 5s0 4d8 9, 5s0 4d10. Very important compound, anomalous, very important. Palladium having S0, very important. Now one second. That's about palladium. Now silver 47, that is 5s1 4d10 normally. Then we have cadmium 48, that is 5s2 4d10. Here technetium and which all elements? Technetium, it skips its half stability, I don't know why, but it's an odd element. And palladium is important. Okay, so next series you don't have to learn, only these two series you learn, only these two series you can learn. Okay, yes. Now they have explained why it is zinc, cadmium, mercury and copernicium is not there. It's not transition element, that we already know. Now let us go with the next thing. Now we have some physical now we are going to learn the properties of D block elements. Properties. First one is physical properties. Okay. In that physical property, first of all, they are telling some unwanted property, that is lattice structure. In this lattice structure, don't learn the lattice structure of all the compounds. Learn some exceptions. That is manganese, Mn, and zinc, cadmium, mercury. These compounds don't have characteristic lattice. They don't have characteristic lattice structure. They don't have HCP, BCP. This BCC, HCP and all many children don't know. Why? Solid state chapter deleted, right? So in that chapter everything is explained, but now we don't know, but we are just learning HCP, hexagonal close backing, BCC, body centered cubic. What one more is there? CCP, cubic closed backing. We are just learning it. So just learn manganese, zinc, cadmium, mercury don't have characteristic lattice structure. This is important. Okay. Yes. And just learn the lattice structure of one compound, that is iron, it is showing BCC, that is body centered cubic. Body centered cubic. Okay, yes, this is about lattice structure. One. Now second one is melting point. So for melting point and all, there are graphs given, so I think we will refer NCERT directly and learn from there. Yes, so here we have the next portion, that is melting point. One second, that is melting point. You know that the compound with highest melting point is tungsten. This is a GK, that is tungsten has highest melting point. The transition metals are having comparatively, with the exception of zinc, cadmium, mercury, are very hard and have low volatility. Their melting and boiling points are high. So first of all, the characteristic here is they have high melting and boiling points. The reason for that is the high melting points of these metals are attributed due to the involvement of greater number of electrons from n-1 d. That is, the reason for this is more electrons from n-1 d subshell plus 4s that ns subshell. Both electrons are involved in interatomic metallic bonding. This is the reason for their high melting points. High melting points. Addition to their ns electron in the interatomic metallic bonding. In any row, the melting points of these metals rise to a maximum of D5, except for anomalous value of manganese and technetium. Look, usually we titanium, look, scandium's group we will never write. From titanium only for Ella property we will start. So titanium, vanadium, chromium, there is a sudden decrease in manganese. Why? That is an anomalous property. Look, here also zirconium, niobium, molybdenum. Suddenly technetium, that is manganese's group, is falling down. Okay, it is what? It is noted. It is a special character. So okay, regularly as atomic number increase, they have a high enthalpy of atomization, which are shown that maxima at about the middle of the each series indicate that one unpaired electron per d orbital is particularly favorable for strong interatomic interaction. In general, greater the number of valence electron, stronger is the resultant bonding. Since the enthalpy of atomization is an important factor in determining the standard electrode potential of a metal. Okay, they are telling that atomization enthalpy is also very high. Atomization enthalpy also high for D block due to unpaired electrons. Look, in middle they are rising to a maximum. Right, due to unpaired electrons. So as unpaired electrons increase, interatomic metallic bonding increase. Why is zinc, cadmium and mercury having a low atomization enthalpy and low melting point? Because they don't have n- what? They don't have free electrons in d subshell. All the electrons are paired. There are no unpaired electrons. That is the reason. Okay, yes. Another generalization that may be drawn from figure 8.2 is that metals of the second and third series have greater enthalpy of atomization than the corresponding elements of the first series. This is an important factor in accounting for the occurrence of much more frequent metal-metal bonding in compounds of heavy transition element. Metal-metal bonding is high. Look, as series, this is first series. Okay, second series atomization enthalpy is once again increasing. Third series it is the most. So as series increasing, atomization enthalpy is increasing. So as we are going down D block, the strength of metallic bonding increases. Okay, this is told. Now let us consider this variation in atomic and ionic size of transition element. Okay, in general, ions of the same charge is in a given series show progressive decrease in radius with increasing atomic number. This is because of new electron enters a d orbital each time the nuclear charge increases by unity. It may be recalled that the shielding effect of a d electron is not that effective. Hence, the net electrostatic attraction between the nuclear charge and the outermost electron increases and the decreases. Same, the many things is told. Okay, look. First transition series is like this. This is the first transition series. Next, second transition series and third transition series are having what? Similar size. You know that as we go down the group, size should increase. But the problem here is that second transition series and third transition series are having similar size. The similar size is due to the poor shielding effect of d subshell and poor shielding effect of what? Poor shielding effect of d electron, and this lead to lanthanoid contraction which gives similar size to second and third transition series. Okay, the net result of the lanthanoid contraction is that the second and the third D series exhibit similar radius. That is, zirconium and hafnium are having similar radius. Zirconium, hafnium means somewhere here. Okay. And have very similar physical and chemical properties, much more than expected on basis of the usual family relationship. The problem is that D block is always having what? Series relationship more compared to group relationship. But the problem is that zirconium and hafnium are like what? Very twins. They are chemical twins. Okay, because they have similar size. They have same character, same physical and chemical properties. Same is mostly same physical and chemical properties. They are called as chemical twins. This is due to the poor shielding effect of D block and lanthanoid contraction. Understand this. Okay. The factor responsible for the lanthanoid contraction is somewhat similar to that observed in an ordinary transition series and is attributed to similar case. That is, imperfect shielding of one electron by another in the set of d orbitals. However, the shielding effect of one f4f orbital by another is less than that of one d electron by another, and as the nuclear charge increases along the series, there is a fairly regular decrease in the size of entire fn orbital. The decrease in metallic radius coupled with the increase in atomic size result in a general increase in density of this element. Thus, titanium to copper, the significant increases density may be noted. Density increases down the group. Here also we can look this table. Atomic number 21, 22. Okay, that we know. Electronic configuration. This one you learn. The other one you can create it simply. Just remove one electron accordingly. Enthalpy of atomization. The element having most enthalpy of atomization is vanadium. I told you something that vanadium. Look, vanadium, and least is for zinc. Okay. Now ionization enthalpy we have not learned, so we will be coming back. Now radius, ionic radius. It should increase, but look. Copper and nickel have 126 similar radii. Copper and nickel is having what? Similar radii. Not copper and nickel, cobalt and nickel is having similar radii. Iron also. No need to learn this order. Understand what? For atomic size, the graph is somewhat like this. Zinc, once again it is increasing. Once again it is increasing. Okay. Density increases across a group. Normally increases across a group, but somewhere in between it's different. So we cannot learn it properly. We can just learn it with a basic idea. This question: why do transition elements exhibit higher enthalpy of atomization? Because of large number of unpaired electrons in the atom, they have stronger interatomic interaction, hence stronger bonding between atoms, resulting in higher enthalpy of atom. That is, As number of unpaired electrons is high, that leads to high metallic bonding. Therefore, more atomization enthalpy. Now next one is ionization enthalpy. Ionization enthalpy. There is an increase in ionization enthalpy along each series of the transition element from left to right due to an increase in the nuclear charge which accompanies the filling of the inner d orbital. This value shows that successive enthalpy of these elements do not increase as steeply as in the case of non-transition elements. The variation in ionization enthalpy along a series of transition elements is much less in comparison to variation along a period in non-transition element. The first ionization enthalpy in generally increases, but the magnitude of increase in the second and third enthalpy for the successive element is much more higher along a series. The thing is that first ionization enthalpy, they tell it is increasing and all. First ionization enthalpy for D block has an odd order. It's given here. Look the first ionization enthalpy order. Okay. It is regularly increasing across the group. So no problem. Regularly increasing across the group. The irregular trend in the first ionization enthalpy of metals of 3D series. Is this an irregular increase? 1 second. I don't know. We'll just read the NCERT part. The irregular trend in the first ionization enthalpy of metals of 3D series, though of little chemical significance, can be accounted by considering that the removal of one electron alters the relative. Why is the first ionization enthalpy in odd order? Removal of one electron alters the relative energy of 4s and 3d orbitals. This is the reason. Now, you have learned that when d block elements form ions, ns electrons are lost before n-1 d electrons. As they move along the period in a 3D series, we see that nuclear charge increases from scandium to zinc, but electrons are added to the orbital of inner subshell, that is 3D orbital. These 3D electrons shield the 4s electron from the increasing nuclear charge somewhat more effectively than the outer shell electrons can shield one another. Therefore, the atomic radii decreases less rapidly. The ionization enthalpy increases only slightly along the 3D series. The doubly or more highly charged ion have DN configuration with no 4s electron. A general trend of increasing value of the second ionization enthalpy is expected as the effective nuclear charge increase because of one d electron does not shield another electron from the influence of the nuclear charge because d orbital differ in direction. However, the trend of steady increase in second and third ionization enthalpy breaks the formation of Mn2+ and Fe3+ respectively. In both the cases, ions have d5 configuration. Similar break occurs at corresponding elements in the later transition element. So they are telling many lot things. We'll just understand that ionization enthalpy increases across a period in the first case because it's given like this. This is the order given. Second ionization enthalpy is having difference accordingly. You remove one electron and look how is the stability. Depending upon that, you can easily write the order. Okay. Now we will read this paragraph. The interpretation of variation in ionization enthalpy for an electronic configuration Dn is as follows. The three terms responsible for the value of ionization enthalpy are attraction of each electron towards nucleus, repulsion between the electron and the exchange energy. Exchange energy is responsible for the stabilization of energy state. Exchange energy is approximately proportional to the total number of possible pairs of parallel spins in the degenerate orbital. When several electrons occupy a set of degenerate orbital, The lowest energy state corresponds to the maximum possible extent of a single occupation of orbital and parallel spins. The loss of exchange energy increases the stability. As the stability increases, the ionization becomes more difficult. There is no loss of exchange energy of D6 configuration. Mn plus S 3d5 4s1 configuration and configuration of Cr plus is 3d5. Therefore, ionization enthalpy of Mn is lower than Cr plus. In the way Fe2 plus has D6 configuration and Mn2 plus has 3d5 configuration. Hence, ionization enthalpy of Fe2 plus is lower than Mn2 plus. In other words, we can say that third ionization enthalpy of Fe is lower than Mn2 plus. I told you, no, you draw the compound, draw the write the electronic configuration and look the relative stability. You can easily find out. The lowest common oxidation state of these metals is +2. To form the M2 plus ion from the gaseous atom, the sum of the first and the second ionization enthalpy is required in addition to the enthalpy of atomization. The dominant term is the second ionization enthalpy, which shows unusual high values for chromium and copper, where M plus ions have the D5 and 3D10 configuration, because second ionization enthalpy of chromium means what it is. It was like this. 1, 2, 3. Very untidy figure. 1 second. Chromium, that is 1, 2, 3, 4, 5. 1, 2, 3, 4. The chromium was like this, right? The chromium was like this. Second ionization enthalpy means this is first ionization enthalpy. Second ionization enthalpy means removing the electron that had stability. So this will be very high. Normal to understand. That way, copper also the same way. So unusually high values for I am reading here. Chromium and copper, where M plus ions have the D5 and D10 configuration respectively. The value of Zn is correspondingly low as ionization causes the removal of 4s electron, which result in the formation of stable 3d10 configuration. That is for zinc. For Zn, it is the compound. The configuration is. I'll write the configuration. That's easy. Configuration is 3s2. Sorry, not 3s2. 4s2 3d10 for zinc. So if I am taking first ionization enthalpy, 1 will be removed from here, so this become 3d1. Second ionization enthalpy, 1 more will be removed, it will be 4s0. Here look, fully filled d subshell, so it is stable. The trend in the third ionization enthalpy is not complicated by the 4s orbital factor and shows the greater difficulty of removing an electron from D5. Look, third ionization enthalpy of zinc means what? Remove one electron from the stable 3d10 and make it 3d9. Then that's the reason third ionization enthalpy is very high. The trend in the third ionization enthalpy is not complicated by the 4s orbital factor and shows the greater difficulty of removing an electron from the D5 Mn2 plus and D10 Zn2 plus ions. In general, the third ionization enthalpies are quite high. Also, the high values for the third ionization enthalpy of copper, nickel and zinc indicates why it is difficult to obtain oxidation state greater than 2 for this compound. Although ionization enthalpy gives some guidance concerning the relative stability of oxidation state, the problem is very complex and not amenable to ready generalization. Okay. Now we are coming to the next factor, that is oxidation state. Learn the common oxidation state shown by every element. Okay, the common oxidation state is but copper and zinc doesn't show +3, but most of the elements show +3. Okay, +3 is one of the common oxidation state. Now let us read it. The elements which give the greatest number of oxidation state occur in the near middle. So the middle of the series, they give most number of oxidation. Example, Mn, that is +7, chromium +6, manganese +7, iron +2 and +3 is the main oxidation state. +6 and only rarely it will give. So look, and middle, Mn is 5. It's correctly at the middle, mostly at the middle. So Mn is having the most number of oxidation state. Manganese, for example, exhibits all the oxidation state from +2 to +7. Mostly the most stable states are +2 and +7 for manganese. Okay, that way KMnO4 minus, that is 1 2 3 4 5 6 7 8 8 minus 1 7. Here it is +7. It is changed to Mn2 plus. You remember this? Yes. So the lesser the number of the oxidation states at the extreme end stems from the either too few electrons to lose and share, or too many d electrons, hence fewer orbitals are available in which to share the electron. The problem is that as the number of unpaired electron increases, more number of electron can be shared and all, because Mn is having how many unpaired electrons, my dear children? 1 2 3 4 5. So there are 5 empty spaces for other electrons to come and join and make the bonds. But in case of scandium, it is only having 1 electron. That means only 1 unpaired electron can come and join. In case of zinc, there is no unpaired electron. In case of copper also, there is no unpaired electron to come and join, right? So the lesser number of oxidation states at the extreme is due to what? Due to less number of unpaired electrons. Thus early in the series, scandium is virtually unknown. Scandium 2 plus is virtually unknown, and titanium 4 is more stable than titanium 3 or titanium 2. At the other end, the only oxidation state of zinc is +2. No d electrons are involved. That's very important. You know one thing. Scandium will only show +3 oxidation state, like that. Zinc will only show +2 oxidation state. That's the thing. +2 oxidation state of zinc. We are getting what? 3D10 4s0. This is the 4s Zn2 plus configuration. Here also d orbital is not involved. That's the reason why zinc was not a transition element. You remember? Yes. At the other end, the only oxidation state of zinc is +2. The maximum oxidation states of reasonable stability correspond in value to the sum of the s and d electrons up to manganese, followed by a rather abrupt decrease in stability of higher oxidation states, so that typical species to follow. Many things are written, not that important. The variability of oxidation state, a characteristics of transition elements, arise out of incomplete filling. Why there are variable oxidation state? The reason is incomplete filling of d orbital in such a way that their oxidation state differ from each other by unity. Example, look, that is they are telling like Zn2 plus. Sorry, what I was doing here. Sorry. So where we are at? Yeah, look. Here you look. Here Mn2 plus 2 plus 1 3 plus 1 4 plus 1 5 plus 1 6 plus 1 7. The difference between the gradual oxidation states is +1. But in case of P block, you just take 1 second. What is this? Yes, sorry. In case of P block, it is like difference will be 2. That is +2, +4, +6 for sulfur. You remember, and -0 and -2. These things were available for sulfur. So they differ by 2. but here they differ by 1. Non-transition element where oxidation state normally differ by a unit of 2. Yeah, it's written here. The next statement, unit by of 2. An interesting feature in variability of oxidation state of D block elements is noticed among groups group 4 through 10. Although in P block the lower oxidation state are favored by the heavier members due to inert pair effect, the opposite is true in the groups of D block. For example, group 6 molybdenum 6 and tungsten 6 are found to be more stable than chromium 6. Thus chromium 6 in form of dichromate acidic medium. So, the thing they are telling us that look, in P block there is a thing that as we go down, look, we are having oxygen, sulfur, tellurium, polonium, selenium, something and all. We are having these elements. Not, we'll take some other group, very bad group. Nitrogen, phosphorus, antimony, bismuth and all is there in this group. Here nitrogen will show highest oxidation state and bismuth is allowing to show lowest oxidation state. But in D block chromium, molybdenum, once again chromium, molybdenum, tungsten. Here chromium wanted to show the lowest oxidation, that is +2, and tungsten wanted to show +6, highest oxidation state, opposite to that of P block. That's being told here. That's the reason why what's happening. Chromium, that's the reason why chromium 6 in the form of dichromate in acidic medium some strong oxidation, oxidant. That's the reason why Cr+6 is being converted to Cr2+ in potassium dichromate in acidic medium, acid. That's the reason why chromium prefer low oxidation state and tungsten prefer high oxidation state. So this is an important statement. Okay, yes. Low oxidation states are found when complex compounds has ligand capability pi acceptor. That this not that important. Okay, this is important. Trends in the M2 plus M standard electrode potential. In standard electrode potential, that is reduction potential from M2 plus to M. So, okay, you know that positive reduction potential means reduction is preferred. Negative reduction potential means oxidation is preferred. In this thing, understand only copper has positive reduction potential. That's the only reason why copper plus once again, so something happened. That's the only reason why copper cannot be liberated by like copper cannot be liberated, cannot be reacted by acids. That is, you know that if I am adding copper to H2SO4, we prefer to getting CuSO4 plus H2, but never this happen. Why? Because Cu will never become Cu2 plus. Only the opposite happens. This is not possible. This is only possible. That's the reason. And that's because why positive electrode potential of copper. Okay. Now the other order is given here. That is titanium, vanadium, chromium. It's increasing. For manganese, the reduction potential is decreasing. Why? We can just check. Why it is having a less reduction potential? We will do Mn2 plus. What is this thing? Electronic configuration. It is 3d 4s0 3d5. This is more stable than M. So this is having half filled configuration. M is having 4s2 3d5. 3d5. Both are stable, but already stable state will transform into another state which is stable, but will it transform? Does it wanted to transform to that state? No, it's unnecessary to transform to that state. Therefore, its reduction potential is low. It wanted to stay in the state that it is now. Okay, yes. Now this thing is observed, and copper is having positive value. These things not normally taken, and here zinc is having a low value because of half filled, fully filled deception. Fully filled deception. Okay. So why does copper is having a high positive value? The unique behavior of copper having positive E naught account for the inability to liberate hydrogen from the acid. I told that only oxidizing acids can react with copper, because oxidizing acid can react copper because copper is a reducing and react with copper, that acid being reduced. The high energy to transform copper to copper 2 plus is not balanced by its hydration enthalpy. The general trend towards a less negative E naught value. Okay. Now why Mn, Ni and zinc are more negative than expected? Okay. Nickel is also having a more, look, nickel, we expected that nickel will have a value, but it is having more value. The reason for high value of nickel is due to look, E naught for nickel is related to the highest negative hydration enthalpy of nickel. High value for nickel. Mn2 plus and Zn2 plus, it is stability. Now trend in the M3 plus M2 plus standard electrode potential. Look, M3 plus M2 plus. We will only look for manganese. For manganese, M3 plus means destroying of its half-filled electron, half-filled subshell. M2 plus means half-filled, so which is stable. Yeah, M2 plus is stable. That's the reason why Mn shows high value of standard electrode potential. Mn3 plus shows high value of electrode potential, and high value for Mn, and zinc also show the same high value because of its deterioration of fulfilledness. Fe3 plus will show a low, Fe3 plus to Fe2 plus. Fe3 plus is having half-filled subshell. Fe2 plus is not having half-filled subshell, so which is preferred? Half-filled is preferred. Therefore, iron will have a low value, and vanadium also will have a low value related to its stability. That is, vanadium have a low value because its stability of what? Half-filled T2G. Okay. Yes. Now trend in stability of higher oxidation state. Table shows the stability of halides with higher halides. The +7 state for manganese is not represented in simple halide, but MnO3F is known, and beyond Mn no metal has the trihalide except FeX3 and COF3. The ability of fluorine to stabilize the highest oxidation state. Fluorine has stability to stabilize higher oxidation state. That is, look, MnF4, CrF6, fluorine can form bonds with the higher oxidation state. Look, because for M, so you will think for Mn plus 7 is the highest oxidation state, so MnF7 should come. This compound is not formed because of some problems with manganese. But if you check, one of the manganese highest oxidation is plus 4 form MnF4. For chromium 6 plus 6 is the highest oxidation from chromium 6. So higher common 4 and F4, VF5 and CRF4 is formed. CRF form is formed. All the VF plus 5 is only represented by VFI. The other halides, however, undergo hydrolysis to give VOX3. Another feature of fluoride is their instability in lower oxidation state. They are unstable in lower oxidation state. In these oxidation state, they are not that stable. Lower oxidation state, they are not stable. And the same applies to CuX. On the other hand, Cu2 halides are known except iodide. In this case, Cu2 plus oxidizes I minus to I2. Okay, it's given here. Now, however, many copper 1 compounds are unstable in aqueous solution and undergo disproportion. The thing is that Cu plus is very unstable. They disproportionate into Cu2 plus and Cu. This is very important. The stability of Cu2 plus rather than Cu plus is due to much more negative hydration enthalpy of Cu2 plus than Cu. Why is Cu2 plus more stable? It is due to higher negative hydration enthalpy. Okay. The ability of oxygen to stabilize the highest oxidation state is demonstrated in the oxides. Here look, Mn2O7. Which one? Plus 7. CrO3. But for chromium, CrO3 is only found. But halide had a CrF6. Right? V2O5. Vanadium's plus 5. Here vanadium's 5 state. VF5 was there. Okay. So these are the compounds. The same thing is written here. So highest oxidation state. If oxygen and fluorine, if you are considering oxygen, one second, it's written here. The ability of oxygen to stabilize these higher oxidation state exceeds that of fluorine. Considering oxygen and fluorine, oxygen has more power to stabilize higher oxidation state. The highest Mn fluoride is MnF4, whereas the highest manganese oxide is Mn2O7. That's the reason. One example. The ability of oxygen to form multiple bonds to metal explain its superiority. This is the reason. This reason is important. It's a multiple bond formation capacity of oxygen is the reason for it. Okay. Yes, sorry. Okay. Yes. Now let us go. Chemical reactivity and E minus E0 values. Transition metals are widely in their chemical reactivity. Many of them are sufficiently electropositive to dissolve mineral acids, although few are noble, that is, they are unaffected by single acid. The metal of the first series, with the exception of copper, are relatively more reactive and oxidized by hydrogen. That is, they can replace hydrogen from a metal, but copper cannot replace because of its positive E0 value. So the rate which metal reacts with oxidizing agent like hydrogen ion is sometimes low. For example, titanium and vanadium in practice. Okay, it's written. The E0 value for M2 plus to M indicates a decreasing tendency to form divalent cation across the series. This general trend towards less negative E0 values related to the increase in the sum of the first and second ionization enthalpy. It is interesting to note that E0 value for Mn, nickel and zinc are more negative than expected from the general trend. This is more negative. For nickel it's because of hydration enthalpy, zinc and manganese because of stability of half-filled configuration. Whereas the stability of half-filled D subshell in Mn2 plus and completely filled D subshell D10 in zinc are related in their For nickel, E naught value is related to the highest negative hydration enthalpy. The same thing what I told is repeated there. An examination of E minus value of redox couple M3 plus M2 plus shows that Mn3 plus and CO3 plus are the strongest oxidizing agent in aqueous solution. The ions Ti2 plus V2 plus Cr2 plus are strong reducing agents and will liberate hydrogen from dilute acids. Okay, noted. Now different question is given. Where is that question? It's not here. You know that Cr3 plus, that is Cr is this compound, like this is Cr. Cr3 plus is more stable than Cr3 plus is more stable than Cr2 plus. Why? Cr3 plus is having what? Half-filled T2G orbital. That is T2G orbital from coordination compound. T2G orbital. That way Cr3 plus is more stable. Therefore, Cr2 plus is a reducing agent. Note it. Okay, or it's a negative reduction potential. It has negative reduction potential. Note it. This is important. This thing is important. Okay. Now magnetic property. There are two properties, that is diamagnetism and paramagnetism. If unpaired electron is there, mostly it will be paramagnetic. Or there are many unpaired electrons, it can also be ferromagnetic. But if there are no unpaired electrons, it is mostly diamagnetic. Okay. Yes. Attracted strongly. So how is their magnetic character? Paramagnetic feebly attracts, ferromagnetic strongly attracts, like the neodymium magnet that we use in our home. Or normal magnets. Diamagnetic substances feebly repel. They slowly repel, not like other north-south repulsion, but like feebly repel. Now the magnetic moment, spin-only magnetic moment of an element can be calculated by this formula, where N is the number of unpaired electrons. We are calculating it in the unit which one? Bohr magneton. One second, why it is looking like this? Yes, we are calculating in the unit Bohr magneton. Okay, yes. The magnetic moment increases with The magnetic moment increases with increasing the number of unpaired electrons. Thus, the observed magnetic moment gives us useful indication about the number of unpaired electrons present in the atom. As number of unpaired electron increases, N will increase. So, maximum number of unpaired electron is 5. That is 5 plus 2, 7 into 2. That is root 35, approximately equal to 5.9. This is the maximum spin-only magnetic moment that can be observed. This is given here. Observed and calculated is given. Note. For manganese 2 plus, we have the most. Second for Fe and Cr, then V2 and CO, then Na and T, then Cu and Ti, then Zn and copper. Noted. Did you note? Yes. That's about it. Now, color formation. Why does D block elements form color? The reason is DD transition. This reason is the only sole thing that you should learn. Why DD transition happening? Due to unpaired electrons. Paired electrons. That's the reason for DD transition. When an electron from lower energy of d orbital is excited to higher energy d orbital, the energy of excitation corresponds to a frequency of light absorbed. That is called DD transition. That frequency of light absorbed is seen by humans. That is DD transition. Different colors are given. Just learn one thing. If there are no unpaired electron, compound will be colorless. This is the only thing you have to know. The other colors they will not ask, but colorless they can ask. Look, scandium 3 plus colorless, Ta4 plus colorless, zinc 2 plus colorless. So yes, that's the thing. Now formation of complexes. Always copper, all the complexes are mostly formed by D block elements because they are having unpaired electrons. Okay, complex compounds are formed by these elements. Okay, very good. Transition metal form many complexes because this is due to the comparatively smaller size of the metal ion, the higher ionic charge and the availability of d orbital. That is, availability of d orbital, small size and high ionic charges. These are the reasons. This is important. These reasons are important. Okay, yes, small charge, high ionic charge, small size and availability of d orbital is the reason for formation of complex compound. Now we have catalytic property. The transition metals and their compounds are known for their catalytic activity. Okay, these activities ascribed to be their ability to adopt. Why they are having this catalytic character? It's due to their ability to adopt multiple oxidation state. This statement, this thing is the most important here. One second. Some examples are vanadium oxide in contact process, finely divided iron in Haber's process, nickel in catalytic hydrogenation, etc. Catalysts at a solid surface involve the formation of bonds between reactant molecules and atoms of the surface of the catalyst. First row transition metals utilize 3d and 4s electron for bonding. This has the effect of increasing the concentration of the reactants at the catalyst surface and also weakening of the bonds in the reacting molecule. Also, because the transition metals that this and all is given, so one example is given, read it. Now formation of interstitial compounds. Interstitial compounds are formed when small atoms like Ca, H, N are trapped inside catalyst lattice of metal. That is, we will be having manganese. Inside these four manganeses you think a nitrogen is trapped, so we call them Mn4n. But this is not in a specific composition and all, we just call them like that. And when hydrogen traps inside vanadium, we call them 0.56. And when hydrogen traps inside titanium, etc. The speciality of this interstitial compound is that we should learn. They have high melting point, higher than the pure metal. They are very hard. They are retain metallic conductivity. They are chemically inert. These four things you should learn. That's what you have to learn. Okay. Okay. Now one alloy formation, that is what brass, bronze, German silver, etc. are different alloys. Mostly these alloys contain D block elements only. An alloy is a blend of metals prepared by mixing the components. Alloy may be homogeneous solid solution in which atoms are one that this and all is given. Why does they form? They form alloy because of similar radii and other characteristics of transition metals. Alloys are readily formed because of what? One reason is lanthanoid contraction. That's the reason they have same property and contraction. They are that's one of the reason they have the similar size. Okay. They have hard and have often high melting point. The best known alloys of chromium, vanadium, tungsten, molybdenum, manganese are used for production of a variety of steel, stainless steel. This is important. Brass is copper and zinc, bronze is copper and tin. This is important. Then German silver is there. That also once asked for the exam. One second. German silver. German silver. So you think it is German silver, so its alloy is silver. In German silver, there is no silver. That's the important thing. We have copper, zinc and nickel. Copper, zinc and nickel in German silver. Now, oxides and oxyanions of metal. Some important compounds. Okay. These oxides are generally found by the reaction of metals with oxygen at high temperature. Okay. Oxides generally found by metal with oxygen at high temperature. All the metals except scandium form MO oxides which are ionic. The highest oxidation number in the oxides coincides with the group number and is attained in Sc2O3 to Mn2O7. Beyond group 7, no higher oxidation state of iron above Fe2O3 are known. Beside the oxide, the oxocation that the synod is given. Okay. As the oxidation number of metal increases, ionic character. This is important. As the oxidation number of the metal increases, ionic character decreases. In the case Mn2O7 is covalent green oil. Even CrO3 and V2O5 have low melting point. In their higher oxidation state, acidic character is prominent. They are mostly acidic. Thus, Mn2O7 gives HMnO4 and CrO3 gives H2CrO4 and H2Cr2O7. V2O5 is however amphoteric, though mainly acidic and give V2O5. Many of them write it as acidic, but it is amphoteric. Though mainly acidic can give VO4 3 minus as well as VO2 plus salt. In vanadium, the gradual decrease. Okay, that thing is not important. Just understand. CRO, the well characterized CRO is basic, but Cr2O3 is amphoteric. So now we are going to learn about some compounds of transition element. That is one, potassium dichromate, K2Cr2O7. Yes, it is prepared from chromator, that is Fe2CrO4. So first of all, into chromator add Na2CO3 and oxygen, it becomes Na2C. FeCr2O4 will become Na2CrO4 and Fe2O3 plus CO2. This is the first step. And take this Na2CrO4 and hydrolyze it. Sorry, Na2CrO4 and acidify it. We get Na2Cr2O7, that is sodium dichromate. We get sodium dichromate. The sodium dichromate, when treated with KCl, we get potassium dichromate. Okay. This Na2CrO4 is a yellow solution. It's a yellow solution of sodium chromate. It's a yellow solution. Okay. Potassium dichromate is a orange. Okay. Yes. So they have given some reactions. So look, this is chromator, that is Na2CrO4. This is chromate. This chromator is given here. Cr2O7 bond is given here. Here you learn this angle between this, that is 126 degree. Here the bond length, it is 179 picometer. Here 163. Here 163 picometer. This bond is important. That is 126 degree. Okay, 126 degree. Learn it. The structures of chromate ion and the dichromate ion are shown below. The chromate ion is tetrahedral, whereas dichromate ion consists of two tetrahedra sharing one corner with the Cr bond of 126 degree. This 126 degree is important. Sodium and potassium dichromates are strong oxidizing agents. The sodium salt has greater solubility in water and is extensively. So you are thinking that why should we take this potassium K2Cr2O7? If we get this Na2Cr2O7, this also having the same characteristic. So why can't we use this? The problem is that sodium salt, that is sodium potassium dichromate, sodium dichromate is soluble in water and greatly used as an oxidizing agent in organic chemistry. Potassium dichromate is used as primary standard in volumetric analysis. So which is the primary standard in volumetric analysis? K2Cr2O7 is a primary standard in volumetric analysis. Okay, yes. Thus acidified potassium dichromate will oxidize. Okay, now the oxidation reaction is given here in acidic medium. It will only oxidize in acidic medium. Cr2O7 plus 14H plus 6 electron give 2Cr plus 7H2O. 14H plus, one second. Cr2O7 plus 14H plus 6 electron gives 2Cr3 plus 7H2O. Okay, and the different reactions are given. Please check it. Now potassium permanganate is prepared by the fusion of MnO2 with an alkali. So take an MnO2, add alkali to it, you get K2MnO4, not Na2CrO4 here. Here we get K2MnO4, that is manganate ion, manganate. That color is dark green, K2MnO4, dark green, which disproportionate in neutral medium. And we are getting this. Okay, yes. But the problem is that we are using MnO2 and we are getting some MnO2 back. So it's a time loss reaction. It's a time loss reaction. So we don't prefer this reaction. We have other reactions. That is, one is this fusion, one is electrolytic changing of MnO4 2 minus to MnO4 minus. Anything can be preferred. In laboratory it is made by this method. One second, why always this right angle triangle is coming, I can understand. Laboratory, this method is used. Now KMnO4 disproportionate into K2MnO4 as a green liquid and MnO2. That's given. Now these three reactions are important. That is, this is in basic and neutral medium. This is in acidic medium. In acidic medium 8H plus 5 electron. Acidic medium. The other medium it is 4H plus 3 electron. This is the thing you should remember. Then others you can do. The thing is that in acidic medium we get I minus will become I2. But in basic medium I minus is going to become IO3 minus. IO3 minus. Yeah. Where is it? Yeah. This thing is important. It's important. And that is the only difference there. That's the only difference there. Now note this. Why can't we use hydrochloric acid while in the present hydrochloric acid when we are doing permanganate titration? The reason is that hydrochloric acid will be oxidized to chlorine by potassium permanganate. That's the reason. That's the reason. So by this, D block elements come to an end. So for D block elements itself, we took a long time. We explained everything clearly. This is not like a revision class. This is a starting class. We can use this as a starting class itself and you can listen to this. Okay. So I think next video we will be doing the inner transition element, that is F block. Thank you.